Welcome to the deep dive. Today we are jumping into something absolutely fundamental, the inner workings of chemical reactions.
We are. We're talking chemical kinetics and its modern application, chemical reaction engineering, or CRE.
And our mission for this deep dive is to trace the history, from the very first time we could measure how fast a reaction goes through the big theories that defined it.
And then we'll leap all the way to today. We'll look at how modern engineering is using things like machine learning and stochastic models to handle just massive complexity.
Okay, so before we get into the speed, we have to talk about the permission slip, right? Thermodynamics.
Exactly. It's the essential difference. You have to distinguish kinetics from thermodynamics.
Thermodynamics is the if.
It's the if, yes. It tells us the direction. Is this reaction even possible? Is there a decrease in what we call Gibbs free energy?
Delta G. If it's negative, you're good to go.
You're good to go. The reaction is favorable. But that's all it tells you.
It gives you the destination, but not the roadmap or the speed limit.
That's a perfect analogy. The speed limit, the how fast, that's all kinetics.
Yeah.
And a critical factor, the thing that controls the speed, is the activation energy barrier.
So the classic example here is diamond, right?
It's the best one. Thermodynamics tells us that diamond is, in fact, favorable to convert into graphite. Graphite is the lower energy state.
That is just the most depressing piece of trivia I think I've ever heard. You're saying my diamond ring is unstable?
Technically speaking, yes, but practically it's immortal.
Okay, why?
Kinetics. To convert it to graphite, you have to break every single one of those carbon bonds. The activation energy barrier is just massive.
So it can happen, but the rate is what, effectively zero?
It's so negligible that it won't happen in the lifetime of the universe. So your ring is safe. That barrier is everything.
Okay, let's unpack how we first put a number on that speed. We have to go back to, 1850? Ludwig Wilhelmy.
Yes, Wilhelmy really laid the groundwork. He was studying sucrose inversion, basically the hydrolysis of sugar and acid.
And he was the first to actually quantify it?
He was. He used an integrated rate equation and found, crucially, that the reaction speed was directly proportional to the concentration of the sugar and the acid.
So he is the one who turned it from just an observation into a real quantitative science.
He did. And then that framework got generalized a bit later.
By Goldberg and Wage.
Cato Goldberg and Peter Wage, in Norway, 1864. They formalized it into the law of mass action.
Which says?
That the force driving a reaction is proportional to the product of the reactant concentrations. It's the universal mathematical engine behind all of this.
And then Jacobus Van Hoff comes along and really synthesizes all of this work.
He does. His studies of chemical dynamics in 1884 was so foundational that he won the very first Nobel Prize in chemistry for it in 1901.
And we should also mention Wilhelm Ostwald.
Absolutely. Ostwald gave us the vocabulary in 1887, the words we still use every day in this field, reaction order and half-life.
Okay, so that handles concentration, but the other huge factor is, of course, temperature. We've all heard that rule of thumb.
Oh, that the rate doubles for every 10 degrees Celsius.
Exactly.
Yeah, that's a massive generalization. It's often true in biological systems, but the real deep understanding of temperature came from Svante Arrhenius in 1889.
And Arrhenius is the one who connected temperature back to that activation barrier we were talking about.
Precisely. He was the one who interpreted it correctly. He showed that the way the rate constant depends on temperature is all governed by that activation energy.
Through his famous equation.
Right, the Arrhenius equation. What it shows mathematically is that when you add a bit of heat, you exponentially increase the probability that any given molecule has enough energy to jump over that barrier.
That makes perfect sense. Okay, so if Arrhenius gave us the why based on energy, then collision theory gives us the physical how.
It does. And collision theory is wonderfully simple. For molecules to react, they have to collide. But not just any collision.
It has to be an effective collision.
Effective. Which means two things. One, they have to hit with enough energy, the activation energy. And two, and this is just as important, they have to have the correct spatial orientation.
They have to be facing the right way.
Exactly. If they have the energy but they're backwards, they just bounce off. No reaction.
So the overall rate is just a function of how many effective collisions you can get.
Right. And this tells you exactly which levers you can pull to change the rate.
Like physical state, for instance.
Yeah.
Or surface area.
Critical. In a heterogeneous reaction, say solid in a liquid, the reaction can only happen at the interface.
It's why you start a fire with kindling, not a giant log.
Perfect analogy. You use finely divided wood chips to maximize the surface area, maximizing the contact points.
Like sherbet powder.
Yes, sherbet is just finely ground acid and sodium hydrogen carbonate. The second it hits your saliva, the huge surface area means an instant, rapid reaction. You get all that fizz.
And more concentration just means more molecules in the same space, so more collisions.
Right. It's why things burn so much faster in pure oxygen than in air. The reactant concentration is 5 times higher.
And then there are catalysts, the ultimate shortcut.
Catalysts are the backbone of the chemical industry. They speed things up, not by brute force, but by being clever.
They offer a different path.
A whole new reaction pathway.
Yeah.
One with a much, much lower activation energy. They change the route, not the start or end point.
Like the catalytic converter in your car.
Exactly. Platinum and rhodium providing a surface that helps convert toxic carbon monoxide into harmless CO2.
So collision theory is great for visualizing, but it's a bit simplistic. It treats molecules like simple billiard balls.
It does. It doesn't tell you anything about the molecular structure, the bonds stretching and vibrating. For that, you need a more rigorous theory.
Which is transition state theory, or TST.
Developed by Eyring in 1935. TST is a huge leap. It says that at the very peak of that energy barrier, the reactants form this unstable, fleeting thing called an activated complex.
The transition state.
Right. And that complex is considered to be in a sort of equilibrium with the reactants. This allows chemists to use statistical mechanics to calculate rates based on the actual molecular architecture.
That's a massive conceptual jump. Okay, but in the real world, in industry, reactions are almost never single steps. They're complex chains.
They are. You get these long chain reactions with highly reactive, very short-lived intermediates. And to analyze those, you need a special tool.
The steady state approximation, SSA.
Developed by Chapman and Bodenstein way back in 1913. The core assumption of SSA feels a bit weird at first.
It assumes the rate of change for the intermediate's concentration is 0, but it exists, right? How can its rate of change be 0?
It's a brilliant simplification. Think of it like a bottleneck on a highway. Cars are constantly entering the bottleneck, and they're constantly leaving it.
So the number of cars in the bottleneck at any one moment is basically constant.
Exactly. The concentration of the intermediate is not 0, but its rate of change is negligible because it's being consumed as fast as it's being formed.
And that assumption makes the math workable.
It lets you solve the overall rate law for these incredibly complex, messy mechanisms. It makes them tractable for engineers.
Speaking of engineers, it's pretty amazing that chemical reaction engineering, CRE, as a formal field, is actually quite new.
It's shocking, really. I mean, until the 1950s, designing these huge industrial reactors was often more of an art form.
You're kidding.
Not at all. The 1950 edition of Perry's Chemical Engineer's Handbook, the Bible of the field, had a section on kinetics, but nothing, absolutely nothing, on reactor design.
Wow. So when did it become a real discipline?
The field really took off in the 1960s, driven by key textbooks. The big one was Octave Levenspiel's Chemical Reaction Engineering in 1962.
And CRE today is just defined by unbelievable scale and complexity, especially in something like industrial combustion.
Which brings us to the modern problem.
Yeah.
The computational cost is just overwhelming.
You mean when you try to model these things?
Exactly. A detailed model for, say, methane combustion, like the NUI-GMEC each 1.0 mechanism, can have thousands of interacting chemical species.
Almost 3,000, I think.
2,759, yes.
Yeah.
And when you try to plug that into a large-scale simulation, like computational fluid dynamics, CFD, the cost doesn't just add up.
It explodes.
It scales exponentially.
Yeah.
Simulating all those interactions in 3D space over time is basically impossible in any useful time frame.
So you need a new approach, a compromise.
You do. And that approach is something called compact kinetic models, or CKMs, often built with machine learning.
And the key here is that these models operate below what is physically real. For methane, that's only about 25 species.
Right, so you have to throw away thousands of details. And the way they maintain accuracy is by trading physical truth for computational speed.
They use a virtual reaction network.
It's a complete abstraction. The nodes and the reactions in the model don't represent real chemistry anymore. Instead, you have these virtual reaction rate constants. Just think of them as weights.
And you tune those weights to get the right answer.
You optimize them so that the simple model's overall behavior-like ignition delay time matches the behavior of the full, complex, true model.
And the algorithm that does this automatically, it's called MLOCK, Machine Learned Optimization for Chemical Kinetics.
MLOCK 1.0 is a beast.
Yeah.
It's a huge automation tool that just systematically fiddles with the virtual Arrhenius parameters, the A, the N, the EA for the key reactions in this fake network.
Until the error is minimized.
Until the tiny model's predictions match the giant model's predictions as closely as possible.
And the result is pretty staggering. MLOCK was able to crush that 2,759 species model down to just 15 nodes.
A 15-node model that still maintains something like 87 to 89% fidelity across a whole range of temperatures and pressures.
And that is finally small enough to be used in those huge CFD simulations.
Now it's tractable. Now you can actually design a better reactor.
Can you give a specific example of that compromise where a rate constant had to be, physically dishonest to make the model work?
A great one is the virtual reaction rate for CH3 plus O2. The optimization showed that to match the ignition delay time at 40 atmospheres, that virtual rate constant had to be increased by almost 150% compared to the value that worked best at 10 atmospheres.
So you're forcing this one fake reaction to do the work of hundreds of real ones that you deleted.
That's it exactly. You're tuning the simplified network to compensate for all the missing physics.
Okay, so we've seen machine learning tame complexity on this massive industrial scale. Now let's pivot to the complete opposite end of the spectrum.
From thousands of species to just a handful of molecules, we're going from deterministic engineering to stochastic biology.
Inside a single cell, gene regulation networks.
Exactly. In these systems, the number of molecules can be tiny. And when your populations are that low, the normal deterministic reaction rate equations just fail. They completely break down.
Because they assume you have, like, Avogadro's number of molecules where all the random fluctuations just average out.
Right. When you only have a few copies of a certain protein, you can't talk about an average concentration. The kinetics are driven entirely by random noise. It's stochastic.
So you need a whole different set of tools. The theoretical foundation is the chemical master equation, the CME.
The CME is, in theory, a perfect description. It describes the time evolution of the probability of the system being in any possible state.
But you can't actually solve it.
It's computationally impossible for most real systems. The number of states just explodes.
So we need simulations, like the stochastic simulation algorithm or SSA.
The SSA, also known as the Gillespie algorithm, is an exact numerical simulation. It doesn't solve the equation, it just simulates the system's trajectory, one random reaction at a time, based on probabilities.
And then for a less intense approach, there's an approximation called the chemical Landevin equation.
Right, the CLE. The CLE is useful when SSA simulations just take too long. It basically takes the old deterministic rate equations and adds a carefully constructed random noise term to them.
To account for the stochasticity of the small population.
Exactly. It lets you describe the statistical properties, like the mean and the variance, without having to run millions of exact simulations.
And when the environment itself is noisy, biologists call it extrinsic noise, the distributions you see get a specific shape, right?
That's right. When the kinetic parameters themselves are fluctuating, the resulting distributions you measure, say in gene expression, often turn out to be log normal, not a simple bell curve. It's a signature of the deep, fundamental randomness of life at that scale. So if you step back and look at everything from the 1850s to today's supercomputers, kinetics is really the thread that ties it all together.
It's the link.
It's the critical link between the theoretical if from thermodynamics and the practical when that governs literally everything from a giant industrial reactor to a single gene turning on inside a cell.
It's really a journey across just staggering extremes of scale. We started with the basic math linking concentration and speed, built up through collision and transition state theory.
And then landed on these two modern frontiers.
On one hand, using machine learning to build these compact, non-physical models just to tame the insane complexity of combustion.
And on the other, using stochastic mathematics to capture the essential unavoidable randomness in biology, where you're only dealing with a few molecules at a time.
So here's a final thought for you to chew on. We talked about how glass is technically unstable. It's thermodynamically favorable for it to become crystalline quartz, but the kinetic barrier is so high, the transition is just infinitely slow.
It's kinetically trapped.
Exactly. So consider this. How many other impossible things in chemistry and materials, maybe even in biology, are only impossible because the activation energy, the kinetic factor, is just too high? Could it be that time itself is just another kinetic variable?
A fascinating question.
Thank you for diving deep with us.